Alright, in this video we're going to talk about Objective 1 from Unit 1, which is average rate of change. Before we get started though, I'm going to apologize for the handwriting. The tablet that I'm using has not synced properly with my computer and the pen is a little laggy, but you'll deal with it. So average rate of change is the first thing we're going to talk about. There are two big ideas in calculus. One is finding the slope of a curve at any time, and the other one is finding the area under a curve. So we're going to start with the first big question. We're going to start with finding the slope of a curve. Now, slope and rate of change are the same exact thing. So hopefully you remember that from your algebra classes in trig, that your rate of change is the slope of a line. They are the same thing. You can use them interchangeably. Now, in calculus, we're going to use the term rate of change more frequently than we're going to use slope. That doesn't mean that we're not going to use the word slope. And we're also going to have another word for all of that stuff called the derivative, which we will get into in Unit 2. But rate of change, slope, like I said, same exact thing. We find it the same way as we always have. So we're going to have 2 points, and we're going to take y2 minus y1 divided by x2 minus x1, and that's going to give us our rate of change. Now we're going to get a little bit fancy with our notation. If you've taken physics, chemistry, you might have seen the Greek letter delta used before. It's a little triangle. So delta just means change. So when we see delta y over delta x, that means the change in y over the change in x. So change in y, if you figure out how far it goes from one value to the next, we're going to subtract. So y2 minus y1 becomes delta y, x2 minus x1 becomes delta x. And ultimately, this is going to turn into a dy dx. So we're going to get rid of the Greek letter delta and we're going to turn it into a d. And that's going to be our dy dx. So all of this stuff that you see is the exact same thing. y2 minus y1 is the same thing as delta y, is the same thing as dy. If you divide it by your dx, you get your rate of change, which is also the same thing as slope. Now, here's where things get a little bit different for calculus. This is all well and good when you're dealing with a line. We want to be better than all the people in algebra and in pre-cal. They can find the rate of change or the slope of a line, so we got to one-up them. What we want to be able to do is find the rate of change or the slope of something like this curve here. Now, if you notice up here, I have the equation of this curve. It's 0.25x squared. And what we're going to want to do is pick any point on here. Let's just say right there. And we're going to want to find the slope of this entire curve at that point. Now, we're not really to where we can do that right now, so we kind of have to cheat. And we're going to cheat by using the slope that we've been talking about for the last couple of minutes. And we're just going to make a line. Let's move this point down a little bit so we can see the line a little bit better. So let's try to find the slope at this point here. So we're going to connect 2 points on this curve and make a line. That right there is called a secant line. What a secant line is just a line that intersects 2 points. So a secant line, sorry about that, secant line intersects at 2 points. So like I said, we want to try to find the slope at just that one point, but we can't really do it yet. We don't have the tools. So what we're going to want to do is estimate the slope using a secant line. Now obviously we can get closer to the actual slope at that point if we take this point here and kind of move it in, 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 and then we can get a really, really good estimation of that slope at that point right there. And what that's going to be is a tangent line. And hopefully you know that a tangent line intersects at only one point as opposed to the secant line intersecting at two. So that's what we're going to have to do for a while, is we're going to have to look at a secant line and try to scoot this point really, really close to where we can say, all right, those 2 points are almost on top of each other. So if we found the slope between those 2 points, we're basically finding the slope at just that point there. So we're going to use our idea from over here, this dy dx thing, to try to figure out what the slope at just one point is. Now, that slope at just one point is that thing that I was talking to you about called the derivative. Now, we're going to be spending a whole bunch of time on derivatives, but all it is the slope of the tangent line at a point. So one of the big questions of calculus is trying to find the slope of a line that touches a curve at just one point. And like I said, we really don't have the tools right now to figure out the actual slope, but we can estimate the slope by using a tangent line. One little bit of notation that you're going to need to know on a couple of the worksheets coming up, if we notice here that our function is called f of x, its derivative can be called f prime of x. So derivative f prime. So we're going to look at real quick how we're going to kind of estimate using a secant line, and then we'll call it quits on this video. So if we go over here, I kind of have a little table set up. T is going to stand for time. M is going to be distance from a starting point measured in meters. So time in meters is what we're looking at on this little table here. So after 11 seconds, we've traveled 9 meters. So that's what's going on here. So we can look at this and we can say, over this 20-second time interval, we've traveled 20 meters. So one of the big things that we need to think about here are units for the derivative. And I think I'm getting ahead of myself a little bit. So instead of saying units for the derivative, we'll say units for the rate of change. So units for the rate of change. If we go back to here, remember that the rate of change is dy over dx. So your y values divided by your x values. So to figure out your units on your rate of change, we want to take the units of our y values, divide them by the units of our x values. So on this little problem here where I want to know what are the units for the rate of change, we need to think about what are my y units. So my y units, we got to think y is the dependent variable. Is time or is meters are dependent? Our dependent is going to be meters. And our x, our independent, is going to be time. In this case, I said it's measured in seconds. So our units for the rate of change are going to be meters per second. Now, how we can use this idea of average rate of change is we can say something like, what is the average rate of change on the interval 0 to 20. So this is interval notation. This is saying the t value of 0 to the t value of 20. So when we see average rate of change, we need to think, okay, that's just the slope we've been doing for a long time. So 20 minus 0 over 20 minus 0 equals 20 over 20, which is 1. And then don't forget your units. Units are very, very important in calculus. So 1 meter per second is the average rate of change. Now, real quick, the other thing that we can look at as far as using the average rate of change, and this is what AP is more than likely going to throw at you, is they'll say something like, estimate, we'll say f prime of 17 using the table. So we're seeing this f prime of 17, and we know that means derivative. But right now, we don't know how to find a derivative. But we know that the derivative, if we go back here, oops, lost my mouse. If we go back here, the derivative is just the slope of the tangent line. So that slope. And we know we can estimate that slope by using a secant line that's really close to it, so using that slope. So if we think about what's going on here, if they want us to estimate f prime of 17, we can find the average rate of change at stuff around 17. So if we look at these 2 points here, and we do 17 minus 11 over 18 minus 16. We're going to get 3. And then don't forget your units, and that's meters per second. So even though the average rate of change over the 20-second interval was 1 meter per second, we know at the 17th second, whatever this particle or this car or this person or whatever it is was moving at about 3 meters per second. So average rate of change is just the slope that you've been finding since Algebra 1. And all we need to know for calculus is how to find our units and how it's going to relate to a derivative. It's not going to give us an actual derivative, it's just going to give us an estimate for the derivative. So that's going to do it for this video. We'll see you next time.